James Frericks of Georgetown and Sandro Orjuela of Bowdoin. Please make sure you're unmuted and take it away.
All right, well, thank you very much. Let me also just set up this laser pointer in case I need it. All right. So this is work that was done with a really talented RU student, Sandro Orjuela from Bowdoin College. So I just want to start out, we're in the era of quantum information science, and there are three sides to quantum information science. There's quantum computing, quantum communication, and quantum sensing. Quantum sensing often gets a little bit of short shrift when we talk about quantum information science. And I want to emphasize that this is actually one of the things that we should be focusing on as physicists. I think we have the best opportunity to contribute to educating more people in quantum sensing. And I think it's critical for physics departments to know now that, you're going to have to act now if you want to actually have a role in QIS instruction, because it's going to be taught to physicists, chemists, mathematicians, computer scientists, and engineers. Physics departments are likely to gain the most students from an engineering disciplines, but I don't think they're going to respond to the way that we teach quantum mechanics with differential equations and so forth. I just don't think that's going to be something that they're going to want to work through. I think it just requires, to increase the accessibility of quantum mechanics, you have to lower the mathematical load. And I've been doing this now for a number of years by using algebraic methods rather than differential equation methods. And I'm going to show you how you do this for the free expansion of the Gaussian wave packet. And I do want to say before doing this that I hope that when you look at this, you're going to look at this and say, this is so different from the way that I do things that this is going to be way harder for the students. But I want you to just keep in mind that being unfamiliar with something does not mean that it's actually difficult. It just means that you're unfamiliar with it. And I'll show you that most of the things I'm doing are really fairly simple manipulations. All right, the key observations we have is a Gaussian wave packet is also a simple harmonic oscillator ground state if I pick the frequency to be tuned to the variance of the Gaussian. And time evolution is the equivalent of applying a squeezing operator because I'm applying a p squared, not a p squared plus x squared. So that turns out to actually be a squeezing operator. There are four fundamental identities you need to use to work in quantum mechanics if you work with operators. One is the Hadamard lemma. I'm not going to read this out for you, but you should be familiar with this. This is the series of nested commutators. The second one is the Weil form of the Baker-Campbell-Hausdorff identity, which holds when the commutator commutes with A and B. And this third one is one that you've probably never seen before. This is called the exponential disentangling identity. This is actually a simplified form of it. It relates an exponential of an A dagger plus A to an exponential of A dagger and A dagger squared. And you get these funny numbers that come out when you do that. It's actually easy to derive this just by working with 2x2 matrices. And at the end of the talk, I've put an appendix that shows you exactly how to do that if you want to see the details of where this comes from. The facts that we use is that we have position eigenstates. So the x operator acting on the x ket is x number times the x ket. And in particular, we write the position operator as a translation operator of the state at the origin. And the real key thing is x annihilates the state at the origin because x equals 0 there. The second thing we use is that the lowering operator acting on the simple harmonic oscillator ground state is 0. All right, this is the position space wave function. I'm using a ground state of a harmonic oscillator that gives me the Gaussian. This term here gives me the momentum, and then this is the time evolution. So we just have to evaluate this. We tune the frequency according to the variance, and we give it a particular velocity. And this is just as a reference, the state of the harmonic oscillator when it has a given velocity is given by this formula. I'll be using that later. That's something that would have been covered already in the class if you're doing it this way. So we take our Hamiltonian, replace it by p squared over 2m. And now I'm going to just multiply by 1. You see this is e to the minus IPX, e to the plus IPX, just multiplied by 1. Then I'm going to group these, recognize this is ready for the Hadamard identity. You apply the Hadamard identity, that just shifts the p by p operator plus p0 number, okay? Now, the next thing I'm going to do is I'm going to take that operator, that state x, and I'm going to replace it by the state at the origin with the translation. I'm going to now multiply by 1 again, because x acting on this is 0, so this is just e to the 0, which is 1. And now I have another Hadamard that just shifts the P. And now I'm going to just group terms. I'm going to take terms that don't have operators out, and I'm going to have a linear term in P and a quadratic term in P. So these are the terms that are just constants. Here's the linear term in P, and here's the quadratic in P. Now, the next thing we do is we use the representation in terms of simple harmonic oscillator to replace the P in terms of A's, and it involves an A dagger minus A squared. Now we're going to use our exponential disentangling to convert that to an A dagger squared. That gives some numbers, this number here and this number here. And now I'm going to use exponential disentangling in reverse because I want to convert that P into an X operator. So I'm going to use it in reverse to now create an A dagger plus A squared. So I get an A dagger plus A, different numbers again. And you see this factor will actually cancel this factor. And now I'm going to again multiply by, I'm going to convert this into an X. And now I'm going to just multiply by 1 over here. And I'm going to recognize I have a Hadamard again. I can evaluate that Hadamard. I get this form. And now we're nearly done. I want to evaluate this object. I want to use BCH to separate the X and the P, but I don't actually want to separate the X and the P. I want to convert to P and A because A annihilates against this. And I'm sorry, I want to convert the P to A and X. X annihilates against this and A annihilates against this. So the exponential factors from the BCH become 1s when they annihilate against those states. And I'm just left with the commutator term. So go ahead and do that. And there you go. Aside from this normalization constant, that is the free expansion of a Gaussian wave packet. The normalization constant you get from that first simple harmonic oscillator form that I showed you, it's just this number. And then you're done. That's it. I don't have to do 3 Gaussian integrals with complex numbers and have complex square roots and things apply and all kinds of stuff that's very easy to make mistakes. The momentum space derivation is even easier because the momentum space wave function of a Gaussian, it doesn't expand, so the derivation is even easier. Why should we do this? I think it builds the ability to work with operator identities, which are very important. It applies the squeezing operator in a new context. Squeezing operators are very important for quantum sensing. And I think it gives a much more physical feeling to the calculation of moving the operators around as opposed to just evaluating lots of different Gaussian integrals. And I think it also makes the material much more accessible to students who are not so used to working with multiple nested Gaussian integrals and so forth. So thanks for listening. We have a paper on this that we've already submitted to American Journal of Physics. And this work was supported by the National Science Foundation. And I will stop sharing and see if there are any questions.
So the challenge is our schedule is very fast with these talks. So I'll encourage people to send direct questions via the chat, and it is a challenge for the authors to manage the chat as well as our schedule. Also, remember that you can go on to the abstracts and download the slides. So with that apology, we have to move on to the final talk.